and then sessions at the end. Okay, thank you. We start. All right. So, welcome everybody. I'm Max Di Penta. I'm backing up session chair here. And this is the session on the fourth session on software testing. We have 4 papers of different types. And the first paper is a journal first paper titled Mutation Analysis for Cyber Physical Systems, Scalable Solution and Results in the Space Domain. So I see some of the speakers. So who is going to present? Please go ahead. Fabrizio.
Okay. Hello? Can you see the slide?
Yes, thank you.
Okay, perfect. So hello, I'm Fabrizio Pastore, and I'm from the University of Luxembourg, and I present our journal first paper about mutation analysis for cyber physical systems. This is a joint work with Oscar Corneo and Lionel Briand. What I present is one of the results of a project funded by the European Space Agency, and this project aims at assessing quality assurance practices and improving them. It involves GomSpace Luxembourg and LuxSpace, who are developers of nanosatellites and microsatellites. The motivation for the project is that software failures have high impact on space missions. And since software testing is the prevalent method for validation and verification of this software, we need to assess if the software is thoroughly tested. Then, since coverage adequacy, structural coverage adequacy is already part of standards, what remains to be done is to rely on mutation analysis. Mutation analysis is well known in our community, and it aims to measure the percentage of injected faults that are detected by the test suite. Unfortunately, the presence of equivalent and redundant mutants affect the pertinence of the mutation score as an adequacy criterion. Also, scalability issues simply make mutation analysis inapplicable to large systems that have test suite that takes hours to execute, like the space cyber physical systems that are our case study subjects and are the systems that are targeted by this project. There are several solutions to address this problem in the literature, but most of them are inapplicable in our context. Also, we lack an integrated pipeline in the literature. So what we did was to develop a pipeline that we called mutation analysis for space software, MAS, and it integrates variations of existing approaches and new solutions. We start by collecting code for the software under test. Then we create mutants by relying on the operators indicated as effective in the literature. Then we compile mutants and we retain the mutants that are successfully compiled. And then we remove the mutants that are indicated as being equivalent and duplicate based on compiler optimization, which is standard practice. Then once we have these unique mutants, what we do is to sample mutants. So we sample mutants, we execute the test case, and we continue like that till we have statistical guarantees about the accuracy of the mutation score. And this is a contribution of our work. So imagine that the true mutation score is around 65%. What happens when you performing mutant sampling is that with a larger number of mutants being sampled, you will have a mutation score that is closer to the actual one. But we do not need to be perfect, so we can start sampling when we are close enough to the actual mutation score. So thanks to statistics, we can compute the confidence interval, which captures a range that has a probability of including the estimated value. And then, therefore, we can apply the fixed width sequential confidence interval method, which is a statistical method, and basically says that you can stop sampling when the confidence interval is small enough. In our case, it is small enough when the difference between the estimated mutation score and the actual one should be at most 5 percentage points. This is the approach. We do not execute the full test suite also, but to address scalability issues, we execute a prioritized subset of the test cases. Then we discard the likely equivalent mutants based on code coverage. Basically, based on our empirical evaluation, we can say that the mutants having the same coverage profile are likely equivalent and should be discarded. Then we compute the mutation score with considering only the live non-equivalent mutants and the killed ones. And then the live non-equivalent mutants can be used, let's say, for further inspection to identify new test cases. This is our pipeline. We implemented it in a tool that was also presented yesterday, and we performed an empirical evaluation. And our empirical evaluation is conducted with the largest industrial case study subjects so far considered in the mutation analysis literature. We have control software and a wide set of libraries. Among the results, what I can say is that compared to uniform sampling and uniform fixed site sampling, the FSAI sampling approach is the one that leads to the smallest set of mutants and provides accuracy guarantees. Then, concerning our solution to address scalability issues, the test cases selection and prioritization alone do not provide tangible scalability benefits, but FSCI provides the largest benefit. So the execution time is reduced by 75% in median in our cases. And when combined with test cases selection and prioritization, the reduction goes up to 80%. Which means that the approach that we proposed made mutation analysis feasible in alpha day if executed with 100 nodes in a grid infrastructure. But the cost for that, it's reasonable for this kind of expensive projects. And without our approach, it will take more than 100 days, okay? So it will be infeasible. To conclude, among the practical benefits, I can say that we discovered also lack of oracles. We reported missing test cases for exception handling code. We detected incompleted verification of math formulae, and we discovered a couple of software faults, which is, let's say, very interesting for this type of project. Like, I mean, the software that we analyzed is currently in space, okay? The ESAIL satellite was launched a couple of years ago. This concludes the presentation. We have a website with all our tools, and the paper is available online. Thanks.
Thanks, Fabrizio. So let's keep the questions for the end. We can move to the second paper. Second paper is a software engineering practice paper, and is titled Automated Visual Testing for Mobile Apps in an Industrial Setting. So who is going to present this paper? Dezi, please. Thank you.
Hello, everyone. I'm Zhu Zhiran from Peking University. I'm glad to present our SCIP paper. Mobile apps have been an indispensable part of our daily life, and automated UI testing is a convenient way to assure their quality before they are shipped to users. However, there are two main challenges hindering automated UI testing for industrial apps. First, industrial apps work on multiple platforms. Second, industrial apps frequently use non-standard UI elements whose internal structures cannot be obtained by platform-dependent APIs. To address the preceding challenges, visual testing arises as a desirable solution. Visual testing identifies UI elements from screenshots instead of accessing platform-dependent APIs. Here is an example of visual testing in Security, where widgets are represented as images. Using screenshots only, automated visual testing is applicable to any platform with no modification or little modification. In addition, automated visual testing is able to handle the non-standard UI elements, as long as the UI elements appear in the screenshots. To make automated visual testing a practical solution for industrial apps, we develop and deploy V-tests. Due to time limit, we only introduce the hardware infrastructure and UI element identification components. More details can be found in our paper. First, let's take a look at the hardware infrastructure. We use a high-speed camera to capture the image of device screens and a robotic arm to execute GUI events such as click and swipe on the device. Next, we select proper techniques to identify UI elements from screenshots. There are numerous UI element identification techniques falling into two main categories. First, deep learning-based techniques use a data-driven approach. They are first tuned on a set of training data and then used to process the screenshots. While they are effective given enough training data, data collection is costly. Second, old-fashioned techniques use image gradient to segment the image and locate UI elements in the screenshot. Old-fashioned techniques are data-free, but they may fail to handle complex UIs. we evaluate 3 deep learning techniques and 2 old-fashioned techniques on 5 scenarios on Taobao. Higher F1 score indicates better effectiveness of the technique. We find old-fashioned technique UIED outperforms others in general, with the highest average F1 score, as shown in the table. However, in addition to general effectiveness, when looking into individual scenarios, we find that deep learning-based and old-fashioned techniques complement each other. Consequently, we can combine them to achieve the best effectiveness at a low cost. Next, we evaluate the effectiveness of automated real testing in terms of activity coverage on Android. Compared to Monkey, a state-of-the-practice testing tool for Android, VTest achieves 87% higher activity coverage with firing 90% fewer events, which demonstrates the effectiveness of automated real testing. Then we examine the factors affecting the test effectiveness besides the UI element identification accuracy. First, we find that runtime cost substantially affects the test effectiveness of VTest. F-test and Y-test achieve similar activity coverage as shown in the table, although faster RCNN substantially outperforms YOLO in UI element identification accuracy. But faster RCNN processes the screenshot far slower than YOLO. Thus, we can improve the test effectiveness of real testing by reducing the runtime cost. Here is an example. Cache test caches and reuses the processing results of the same screenshot, which reduces the runtime cost of VTest, and consequently, it improves the test effectiveness. We deploy VTest internally at Alibaba Group and externally at Software Green Islands, China. VTest is used for both user experience testing and functionality testing. Here we list the most important lessons learned from developing and deploying VTest. First, we should embrace the non-deep learning techniques and their integration with deep learning ones to achieve the best effectiveness with low costs. Second, we should pay attention to improving the infrastructure support in addition to algorithm improvement in practice. In this paper, we raise the awareness of the importance of real testing for both industrial and the research community. We propose VTest and design proper techniques to instantiate it into a practical solution for industrial apps. We report the experiences and lessons learned from deploying and developing VTest. Thanks for listening.
Thank you very much. Okay, so we also, in your case, will keep a question for later. We move to the third paper. Third paper is titled FADA Test, Fast and Adaptive Performance Regression Testing of Dynamic Binary Translation Systems. And this is a technical track paper. Please. Jimbo is going to present.
Yeah, okay. Hello, everyone. Today, I'll be introducing our recent research work, FADA Test, Fast and Adaptive Performance Regression Testing of Dynamic Binary Translation Systems. I'm Jing Wu. My collaborators include Jian Dong, Ruili Fang, Wen Zhang, Wenwen Wang, and Decheng Zuo. This is a joint research work by Harbin Institute of Technology and the University of Georgia. Let's first take a look at what dynamic binary translation is. In general, dynamic binary translation, or DBT for short, translates the guessed binary code to the host binary code. Here, the guessed and the host can be different architectures. For example, with DBT, we can execute native ARM applications on an x86 machine. Thus, DBT can enable many important applications. For example, product translation, mobile computation offloading, and so on. However, DBT systems are extremely complex because they need to bridge the semantic gaps between different architectures. The translation and emulation also bring significant overhead. Besides, the code base is very large, and it is updated very frequently to support more features. So, to monitor and maintain the performance of a DBT system, it is necessary to compare the performance before and after each commit, which is known as performance regression testing. Unfortunately, it is not easy to apply frequent performance regression testing for DBT systems. To understand why, let's see how the performance of a DBT system is tested. A widely applied approach is using standard test benchmarks, which are well designed and the testing results are accepted by the state-of-the-art. However, due to the performance overhead of DBT, using the standard benchmarks for performance testing takes a very long time. Another problem is DBT runs on different hardware platforms, from low-end IoT devices to powerful high-performance servers. So using the same benchmarks for different platforms may lead to either long testing time or inaccurate testing results. To address these difficulties of applying performance regression testing for DBT systems, our idea is generating fast and adaptive test programs by learning from standard benchmarks. This approach first learns the behaviors of standard benchmarks and then reconstructs test programs. Afterwards, these test programs can be used for performance regression testing of DBT systems. Based on this approach, we design a testing framework called FADA test. The first design issue of FADA test is what behaviors to learn. To preserve the characteristics of the original benchmarks, FADA test learns the instruction execution behaviors and the thread activity behaviors. Then, FADA test generates test programs by reorganizing code blocks and recovering thread behaviors. Here is an overview of how it works. The first step is profiling the hotness of executed code blocks. Next, thread activity behaviors are also extracted. And finally, with the above information, FADA test is able to generate more efficient test programs. We also implemented FADA test and conducted an evaluation. Now let's see some results. First, above effectiveness, the curves indicate the performance changes among DBT versions. As we can see, FADA test produces very similar results to the original tests. Next is the testing efficiency. The speed ups are shown in this figure. We can see significant testing efficiency improvement. To summarize, the performance issues discovered by the original benchmarks, which takes a very long time, the performance issues can also be discovered by FADA test, while the testing efficiency is also improved. This is my presentation, and thank you for listening.
So just a reminder to everybody, please free to start writing session to the various speakers in the chat. Otherwise, you can still ask questions directly by voice after all the talks. So we move to the next paper. Next paper is again a technical track paper, and it's titled Repairing Order-Dependent Flaky Tests via Test Generation. Okay, any of the authors here? Yes. Changpeng Lu is going to present. Thank you.
Yes. Hello everyone. My name is Changpeng Li, and our paper name is Repairing Order-Dependent Fact Tests via Test Generation. We are Chen Guangwen and August from the University of Texas at Austin. Order-dependent fact test passes in one test order called the passing order, but it fails in another different failing order. In this case, test 1 passes when wrong before test 2, but it fails in another different order when wrong after test 2. In this case, test 1 passes and fails when run on the same code version. Thus, test 1 is a flaky test. And test order is not guaranteed in Java unit tests. Thus, test 1 indeed happens and will mislead the developers about the correctness of their codes. And for why test 1 fails when run after test 2, is because they have some shared state. Test 2 modifies part of the state that test 1 depends on to pass. We refer to the shared state to be the pollution. Test 2 is the polluter and test 1 is the victim. Of shared states, static fields, file system, and database. And in Java code, static fields are found to be the most common type of shared states. Thus, we focus on static fields in our work. We propose order pair. It's an approach to generate patches for order-dependent flag tests. It firstly identifies the polluted static fields and then searches for the potential reset methods that can interact with the polluted state. Then it uses automatic test generation tool to produce the test that uses the reset methods to reset the shared states. Order pair takes the victim and the corresponding fitting order as the input and passes through two main components, the debugger and the generator, to generate the final patches to make the victim pass. We firstly talk about the debugger. The high-level idea of the debugger is to find the polluted static field. What we do is to capture the state before the victim in both the passing order and the fitting order, and then find the polluted static field. When capturing the state during the fitting order, we will load all the static fields in the loaded classes after running the polluter and before running the victim in the fitting order, and then serialize them into XML file for later use. When capturing the state during the passing order, we cannot do it in the same way, because if the victim is the first test to run, all the classes that the victim depends on has not been loaded yet, because Java uses lazy class loading. Thus, we propose a new passing order to run the victim twice. At this time, we will still capture all the static fields in the loaded classes after running the victim once in the passing order, and then serialize them into XML file for later use again. After obtaining the XML file for all the static fields, we will make a difference for each of the XML file for the static field. If they are different, we will investigate this more and output them as different fields. After obtaining the different fields, we will deserialize the XML file of the different fields and loading this part of the state after running the polluter in the fitting order. If it can make the victim pass, we will output this static field as a polluted static field. And then we will talk about the generator in the second part. The generator contains three main components. The reset finder will search for reset methods that can interact with the static fields, with the polluted static fields. Then we will use test generator to generate some method call sequences that use the reset methods, like this generated tests. After obtaining the generated tests, iFix package will apply it between the victim and the polluter and minimize the statements in the generated test to generate the final patches to make the victim pass. As for the evaluation of the debugger can identify the polluted static fields for 181 out of 327 victims. As for the evaluation of the generator, order pair can generate patches for 141 order-dependent flag tests out of 181 order-dependent flag tests, which the debugger can identify the polluted static fields. The baseline iFix package can generate patches for 135 order-dependent flag tests. To conclude my presentation, order pair can identify some polluted static fields and generate patches for them. Compared with iFix package, order pair can exclusively generate patches for 24 order-dependent flag tests. We believe we can firstly apply iFix package. If there are no cleaners, we will apply order pair. We believe these two techniques can be used complementary. You can check our code and script at this link. Feel free to email me if you have any questions. Thank you very much.
Okay, so we go to the next paper. Also, it's a technical track paper, and it's titled Controlled Concurrency Testing via Periodic Scheduling.
Okay, hi everyone. My name is Chen Wen. I'm going to talk about controlled concurrency testing via periodical scheduling. Controlled concurrency testing is a technique for testing concurrent programs. It controls the order in which threads get executed and explores the space of possible interleaving to detect bugs. There is a good number of existing work. They can be divided into systematic testing and non-systematic testing. Despite of their researches limitation and challenges remain for state-of-the-art controlled concurrency testing technique. In terms of controlled scheduling and schedule space exploration, many different ways to achieve controlled scheduling are used in existing work. Some approaches require serializing a concurrent program or injecting sleeping delay to interfere with the thread interleaving. They will introduce high overhead, making fewer interleaving can be tested in a limited time. Real-world programs also use a plethora of synchronization primitives. The preempted way could have pathological interaction with the synchronization in the target program, leading to false deadlock. The challenge is how to achieve better control scheduling. Another aspect is about schedule space exploration. Exhaustive enumerating all possible thread interleaving is often practically infeasible. The number of thread interleaving grows exponentially with the number of threads and the length of program execution. Randomized techniques only provide probability guarantee of finding bugs. Systematic techniques tend to go through a larger schedule space than needed, requiring more overhead or missing some bugs. Thus, the challenge is how to effectively explore the schedule space. To address the two aforementioned challenges, we propose a novel systematic controlled concurrency testing technique called PERIOD. It achieves better control scheduling in an efficient and non-preempted way. And it also achieves effective schedule exploration through 4 key techniques. Let's take a quick look at the workflow of PERIOD, which contains 3 main components: schedule generator, periodical executor, and a feedback analyzer. Given the source code of the program, PERIOD first applies static analysis to identify key points. Key points are the statements that are key to the program observable behavior, such as the statement assessing shared memory location or synchronization primitives. The schedule generator generates schedule according to the number of key points. A schedule is a series of execution phases that contains thread identifiers. The schedule generator employs a schedule bounding technique to systematically generate schedules that are likely to induce bugs. The periodical executor uses a series of periods to host the execution. It enforces the generated schedule in the execution. The feedback analyzer makes use of runtime information such as key points, dynamic key points lines, and a schedule prefix to guide the schedule generator to effectively generate legal schedule. We also design a parascheduler. The parascheduler allows the isolation of specific order on a field statement while letting the rest of the program execute concurrently. This optimization makes it possible to reduce the schedule space to explore. We have implemented our approach in a tool and performed a thorough evaluation. For comparison, we have selected 6 well-known and representative controlled concurrency testing techniques, and 2 recent work that use predictive analysis, and also 3 race detectors. The results show that PERIOD successfully identify more bugs than other competitors. We also include both versions of PERIOD, equipped with our parascheduler and without the parascheduler. With the parascheduler, PERIOD explores schedule space more effectively, allowing more bugs to be detected. The results also show that both versions of PERIOD outperform the other control concurrency testing technique in terms of concurrency bug finding ability. In summary, we present a control concurrency testing technique called a period. It achieves better control scheduling and more effective schedule exploration. It outperforms state-of-the-art control concurrency testing technique, and you can try our artifact out from this link. And that's all. Thank you.
Thanks a lot. We go to the last but not least paper in this session, again, a technical track paper, which is about fuzzing, and it's titled BD-Fuzz Integrating Behavioral Diversity into Generator-Based Fuzzing.
Yeah, so hello everyone. My name is Wang Longyun, and I will be presenting our work BD-Fuzz. And this is joint work with my advisor Lars Grunske, and we're both from Humboldt-Universität zu Berlin. So in our work, we are targeting the problem of behavioral diversity. How can we produce test inputs that not only trigger many behaviors, that is, have high coverage, but also trigger them evenly often with diverse inputs? To illustrate this problem, let's consider the following three execution profiles, where the x-axis represent individual branches and the y-axis represent branch hit counts from unique execution traces. The different profiles could correspond, for example, to individual fuzz campaigns from different fuzzers, or they could also be the result of the same test suite executed on subsequent versions of the same system. And what we can see is that while all execution profiles have the same branch coverage, the branch hit count distribution becomes increasingly uneven from left to right, or less diverse. And this can be problematic because a high unevenness could indicate that most of the testing budget is wasted, exercising the same uninteresting behaviors over and over again, instead of distributing it over all branches in order to increase the confidence in the overall correctness of the system under test, and not only of specific behaviors. Our approach, BD-Fuzz, addresses this problem by leveraging a particular way to produce test inputs, that is, using imperative generators, which depend on a sequence of decision parameters to produce structured test inputs, which could be binary trees, as in this example, but it could also be structured XML files or JavaScript programs. And our key insight is that by analyzing the internal structure of these generators, we can classify these decision parameters into two types. First, we have structural decision parameters, which influence the structural properties of the input, like the numbers of nodes in the binary tree. And then we have value decision parameters, which correspond or fields in the input. So in this example, this would be the node values of a binary tree. And based on this insight, by controlling either type of parameters only, we can perform more fine-grained and controlled mutations in the input space. To illustrate, on the one hand, by mutating the structural parameters only, we can perform structure-changing mutations in the input. So in this binary tree example, this would correspond to mutating the shape of the binary tree. On the other hand, by controlling the value parameters, we can perform structure-preserving mutations in the input. So in this case, we would be performing mutations on the node values while keeping the shape of the binary tree. And BD-Fuzz utilizes these two types of mutations in the following way. So first, BD-Fuzz searches for interesting input structures in the space of semantically valid inputs through structure-changing mutations, and then it performs structure-preserving mutations in order to diversely test particular behaviors that are triggered by specific input structures. And BD-Fuzz integrates this idea in a feedback-guided fuzzing loop in order to produce test inputs that not only increase coverage, but also improve the diversity of the branch execution distribution. As for evaluation, in order to measure the behavioral diversity of a fuzz campaign, we propose to use Hill numbers, which is a popular diversity index from the field of ecology. And in particular, we compute the Hill numbers over the branch hit count distribution. And the metric incorporates both the number of covered branches as well as their relative hit counts over all unique traces. And an important property of this metric is that for different orders of cube, it can be mapped to known metrics such as branch coverage or Shannon entropy. And what makes this metric useful is that it gives us a more insightful exploration profile of a fuzz campaign. For instance, it would enable us to quantify the exploration bias towards particular behaviors. We have evaluated BDFuzz on these metrics against different approaches and have found that while BDFuzz not only improves coverage from the majority of benchmarks, it also significantly improves behavioral diversity across almost all benchmarks. However, we did not see an improvement with respect to bug finding, and this could be attributed to the fact that BDFuzz mostly improved the diversity of the code that has already been extensively fuzzed by prior approaches. Therefore, our approach may be more suitable for testing previously unfuzzed code or recently changed code. And this brings me to the end of my talk. Our tool and evaluation package are available on GitHub and Zenodo. Feel free to check it out. Thank you.
Okay, thanks a lot. So now the floor is open for the questions. So is there any question being asked by voice at this point to any of the speaker? Otherwise, yes, please. Okay, maybe, well, in the meantime, I would like, first of all, Fabrizio to discuss a little bit, because I've seen Fabrizio was replying by chat to a question, but for the interest of the audience, it would be useful to better discuss this point. So the question from Champeng was about the selection and the choice of the prioritized subset of tests.
So thanks. So basically, what we did was to rely on a combination of some ideas that we have seen in the literature. And so the rationale behind our choice is that basically, to kill a mutant, ideally what you want to have is that basically the mutated statement should be covered with values that differ from each other. This is the way, because if you use the same value to cover a mutated statement, of course, you will not kill it the first time, you will not kill it the second. Then it's not doable to trace all the values that go through a mutated statement, because that will be an overkill for the execution, especially when you have a real-time system like our case study subjects. So the idea that someone else had in the past is that usually when you have a different value that flows through a statement, such difference will reflect in a different behavior of the software. Which means that in practice, at a certain point after the execution of the statement, if a value was different than the previous one, you will have a difference in the code coverage, basically. Which means that if the values that cover a certain statements are different, then you will see in the execution of the test case a large difference in what is called a coverage profile of the test cases. So basically, if two test cases cover a same statement with different values, their code coverage, let's say the hit count for the program, for all the statements in the coverage, will be different. And so we rely on this idea. So basically, relying on this idea, okay, first we select a test case that covers the mutated statement a lot of times, which means that anyway it is covering it with a lot of values. So we increase the chance of killing it with the first test case. And then we select test cases that differ from the previously selected ones in terms of these coverage profiles. So basically, we computed the difference in terms of coverage hit counts with respect to test cases already selected. We rely on the cosine distance for that. And then basically we prioritize the test cases according to this idea. And when all the test cases not selected yet do not differ from the previously selected ones, then we don't need to execute them, because anyway they show the same coverage profile, and according to our heuristic, they will not be be useful. So this is basically the idea for our selection and prioritization. I hope to have clarified it.
Okay, yes. And then there was another question about the typical number of sampled mutation that is necessary to achieve statistical significance.
Yeah, well, basically, this somehow relates to the theory of statistics, and it's around 360. So
Always the same number.
But it's not always the case. It's not always the case. And the good thing of what we did is that, with respect to previous work, in order to have a number that always guarantees, the significance, when they're saying, okay, use 1,000 mutants, but it's too many, okay? And sometimes it's enough to have less, and so we have these. Let's say continuous, assessment of the quality of the results, so that we can stop the sampling before. And this is, I would say, our key contribution, because I didn't see it before in previous work in the literature, so that you can decide at runtime when to stop.
Okay. Then can you share?
No, okay, I think so. Max is cutting out, but yeah, I can answer the question. So basically, these parametric generators, we have added annotations to the implementations that were already included by the baseline implementations. So from the original authors, I think they mentioned that writing such a parameter is pretty straightforward, because for them it took around 8 hours, or like 1 working day, to write the full implementation for one file format. And the idea of writing these parametric generators is also to have it as simple as possible. So and let the fuzzer search for the right inputs. And regarding the question whether it can be synthesized from the input format grammar, depends. If it was a formal grammar in a standard specification language, then I think it would be possible to write a general generator that could handle all grammars of the same format, and like a general purpose generator. But if the input format is more complex, like a binary format where you have some more semantic constraints, then I don't think it can be synthesized yet, trivially. So there's still some manual work that needs to be done.
Thank you. If there are no other questions, in the meantime, I take the opportunity to ask a couple of questions around. First of all, I have a question for the second paper, the paper about visual testing of Android. Given the setting that you devise approach, would it be possible to set up this integration? I was asking to the second speaker. I don't know if. Oh, okay. Can you hear me now? Oh, Jesus.
Okay, yes. Yes, we can.
Now you can hear me. So, have approach with.
Sorry, I can not hear the question clearly. Maybe you can type it in the
Sorry,
chat.
and
and
I
I
try to
can-
connect. I tried. Yes. Can you hear me better now?
Yes.
Okay, so was about your setting, and given your setting, assuming I would like to set up a continuous integration pipeline for the Android apps, how complicated will it be?
It's good questions. Currently, at Taobao, we do not adopt a CI process because UI test cases are highly flaky in Taobao. So we simply use a normal test automation process. To make it possible for continuous iteration for UI testing, we should first address the flaky tests, which we plan to investigate in our future work.
Okay, thank you. Then there is also another question for you from Fabrizio. How easy is to apply the approach to a new app? So does it require? Yeah.
Okay, thanks for the question. It's a really good question. It do not require a training phase to apply our approach to a new app because we do not depend on deep learning based technique that need training data. Instead, our main technique, including the UI element identification techniques, is mainly based on an old-fashioned computer vision techniques that are data-free. So our techniques, our system can be easily applied to a new app without any training phase. But the training phase can be used to improve the deep learning component in the system, which can make the performance better.
Okay, thank you. Other questions? Not yet. Okay, I have a question for Fabrizio. So, Fabrizio, did you also define some specific mutants for the space domain, especially higher order mutants, or did you apply conventional mutants for the programming language that is behind?
No, we just applied the conventional mutants. The reason is that, let's say, we would have had to study another programming, what higher order mutants to mutate. Let's say that the feedback that we got from the engineers is that they would have liked, let's say, some mutants that were more high level, but more semantic, you know, like a big mistake in the implementation, but then how to automatically do it, that's not trivial, because we know the problems of mutation analysis, that, you know, the type of change that you inject are so small that in the end, when the engineer has to figure out why doesn't have a test case that cover the mutant, then, you know, it's not always that obvious why that test case is really useful, right? Because sometimes it is obvious, because if the new input that you suggest to use is okay, it's covering a boundary condition that you were missing, then okay, it's okay. But sometimes it's not obvious. But we didn't solve the problem. But we are lucky because the project had a follow-up project, so we have 2 more years to go. So we may study the problem in the coming
because
year.
in some domains people define higher order mutants. For instance, we did for Android. Other people have done for deep learning, and very likely also for CPS. Well, for some CPS domain, it will be possible to define those new data.
The problem is that the applications are so diverse. For example,
Yeah.
our case studies range from network libraries, utility libraries. Then we have a big controller that is basically includes also, let's say, the business logic, and then it becomes a little complicated how to handle it. The interesting point is that we know that if you want to go with easy to use mute operators, you should go with the deletion ones. And also an interesting feedback that we received is that what is useful are the deletion operators working on the different terms of mathematical formulas, or the ones that are deleting the mathematical operators. Because for that, for example, standard code coverage is not enough, right? Because, I mean, when you have a mathematical formula, just covering the formula doesn't mean anything. But maybe you want to be sure that you have covered all the different, let's say, combinations of the input that you want. So, I mean, you don't want to have tested only idempotent cases. I mean, you don't want to test only inputs that do not have any effect on the formula. And for that, the deletion operators are good.
Thank you. Okay, I would like to reiterate a question from Huang to Jinwoo. They discussed it on the chat, but it would be useful to discuss by voice in the interest of everybody. Can you give more information on how you identify the hot code parts? What characteristics will make a block more hot than others? Please, Jin.
Yeah, actually, we identify the execution behaviors of the target benchmark by developing a specific tool, which is based on Intel Pin. We count the execution times of each basic block and then do a ranking. So with this, we can identify the hottest blocks. And in the meanwhile, the hottest blocks are more representative for our next step, the test program generation. So we also use the thread information of the basic blocks, which is which basic block executes how many times in which thread. We also record this information. This would help our test program generation to generate a test program more like the original test benchmarks in terms of thread activities. Yeah, I hope this could answer your question.
Thank you. Okay. Okay, any other question? I have, yes, no. Okay. I have a question for the last speaker. So from what I understand, you have two types of operator. One is non-structure preserving, and another one is structure preserving. So now I totally understand how the structure non-structure preserving operator can help to achieve higher diversity in terms of tests. Now, going to the structure preserving one, sometimes it just happens that you try to change values, but you don't know where to go because of the shape of the landscape of the search space. So how frequently this happens? So basically, you mostly have to apply structure preserving changes, but this does not help to improve the diversity. So I'm curious whether this happens and whether search base could be a better choice in that case.
Yes, so thanks for the question. This depends, as we have observed that this depends on the benchmark subject. So for some subjects, structure preserving mutations would improve diversity of test cases. And for other benchmarks, it would not improve because coverage would be same and nothing interesting to gain there. So what we do is that we use an adaptive approach when choosing structure changing or structure preserving mutations. So we also record program feedback, which tells us whether the mutation resulted in an interesting new state. So if we observe during fuzzing that structure preserving mutations do nothing because the search landscape is just uninteresting, then we resort to performing more structure changing mutations. So we try to use an adaptive approach in order to mitigate this problem of exploring a flat landscape with structure preserving mutations.
Thank you very much. So as promised and as needed, I'd like to close the session now, like 5 minutes before the schedule. So you have 5 minutes to switch to other session. And I also have to chair another session right after as a backup chair. So thanks everybody, and especially congratulations to all the authors. Thank you very much.
Yes, thank you.
Thank you.